So we will continue with the propagation of electromagnetic wave at oblique incidence. Next we will see the representation of wave for oblique incidence, and this is a standard representation of electromagnetic wave under oblique incidence, that is E is equal to E naught x ax plus E naught y ay plus E naught z az into exponential j omega t minus kr. This is how you are going to represent the electromagnetic wave under oblique incidence, where k is a propagation vector and it is represented by k equals kx ax plus ky ay plus kz az, where you know kx, ky, kz represents a propagation vector along x-axis, y-axis and z-axis respectively, and beta gives you the modulus of your propagation vector, which is equal to square root of kx square plus ky square plus kz square. Beta is known as phase constant or sometimes wave number or propagation constant, and r is your position vector, which is defined as x ax plus y ay plus z az, where x represents your x coordinate, y coordinate and z coordinate, and ax ay az represents its equivalent unit vector along x, y and z axis. So this is also expression is important, how you are representing electromagnetic wave for oblique incidence. Okay. Next we will see the conditions that must be satisfied for all values of x and y for EM wave under oblique incidence. Now these are the three conditions, that is, the angular frequency of incident wave should be equal to that of the reflected wave, should be equal to your transmitted wave, and this is known as frequency matching condition. And the second one is the propagation vector of incident wave along x direction should be equal to the propagation vector of the reflected wave along x, which should be equal to the propagation vector of transmitted wave along x direction. Both these terms should be the same, which is ideally represented as kx. Similarly, the propagation vector of this incident wave, reflected wave and transmitted wave along the y-axis should also be the same, which is commonly represented as ky. And this second and third conditions are known as the phase matching condition. And also you can see the second and third condition states that the tangential components of the propagation vector are continuous. Okay, that are continuous. So these are the three conditions that has to be satisfied for all x and y components of your EM wave when it is falling under oblique incidence. I repeat, that is omega I should be equal to omega r should be equal to omega t, which is your frequency matching condition. Similarly, kix should be equal to krx should be equal to ktx. Similarly, kiy should be equal to kry equal to kty. And these three conditions are very, very important in the case of our oblique incidence. Okay. Now again I am drawing the figure for parallel polarization. Okay. So here I am assuming x z to be the plane of incidence. So this is my first medium, this is my second medium, and magnetic wave is incident in this direction. Ki is the propagation vector and it is getting reflected. Kr is a propagation vector of reflected wave and it is getting transmitted, where kt is the propagation vector of the transmitted wave. And theta I, theta r, theta t are the angles which these three vectors make with respect to your z plane. So now Here I have drawn the diagram for parallel polarization. So parallel polarization means components will be parallel to x-axis and z-axis, because here you can see xz is our plane of incidence. Now what I am going to do is, k is our propagation vector. Now I am going to resolve this k into two components. Since it is a vector, you know it can be resolved into two components, and that two components are kix, which is parallel to my x quadrant or x plane, and kiz, which is parallel to my z plane. So I have resolved ki into two components, kix and kiz, where kix is parallel to x plane and kiz is parallel to my z plane. Similarly, I am resolving it for reflected wave and transmitted wave. Here also you can see reflected wave krx is parallel to the x plane and krz is parallel to the z plane. And you know that this reflected wave and incident wave are opposite to each other. That is why here kix is and kiz is taken along this direction, and here krx and krz is taken along this direction. Okay. It is exactly opposite. The perpendicular component, that is this component, will not change its direction when it gets reflected. Okay, but this component will change its direction when it is getting reflected. That is why here it is drawn as minus krz and here it is drawn as kiz, but x components remains the same, only the z component is changing its phase. Okay, now coming to transmitted wave is same as that of your incident wave. There is no change in phase or direction. So it is drawn similar to our incident wave, that is ktx is drawn here and ktz is drawn along this direction. And you can see ktz is parallel to my z plane and ktx is parallel to my x plane. So this is a parallel polarization. So I repeat, first I have drawn ki, which is my incident vector propagation, and I have resolved into two components, kix and kiz, which are parallel to x and z plane. Similarly, I have resolved my reflected wave propagation vector into two components, krx and krz. Similarly, transmitted wave is resolved into two components, ktx and ktz. And another point to be kept in mind is incident wave and transmitted wave will be along the same direction, but in the case of reflected wave, the z component will change its phase. That is why here it is kiz and here it is minus krz. Okay. Now what I have drawn is this. Now this is theta I, so I can draw this also as theta I. Okay, this is two parallel lines, and you know this angle and this angle will be same. Similarly, this angle and this angle will be same. Similarly, this angle and this angle will be same. Similarly, this angle and this angle will be same. Similarly, I can say this angle, this will be same. This and this will be same, right? You might have studied the angles between two parallel lines. Based on that theory, now I can draw this. You just assume this as a parallel line, this as a parallel line, and this as a line intersecting these two parallel lines. Okay, so these two lines. So if this is theta I can say this is also theta I. This is similar to these two angles, this one. So this is theta I and this is theta I, which have this theta I is this one and this theta I is this one. Okay, so if this is theta I, then you know this is also theta I. and that theta, this is this angle theta I. Okay, so I have drawn theta I here. Now similarly I have resolved the components for KRX and KRZ, and here I have marked it as theta R, this angle, and similarly theta T is also marked here, theta T. All theta R and theta T are also drawn based on this particular concept. Okay, so now next point that you have to keep in mind is, if you are having any vector, let it be E or A, whatever it is, A, you know it can be resolved into two components, that is a parallel component and a perpendicular component. And suppose you are marking an angle theta here, then you should keep in mind that that component will be the cos theta component and the other one will be the sin theta component. Suppose you are drawing like this. This is your E, this is your E, and here you are drawing theta. Okay, you just assume here you are drawing theta, and these two are the two components of E. One is your horizontal component or another one is your perpendicular component. Then here theta is this angle, so this will be your E cos theta, and this will be your E sin theta. That you have to keep in mind. Okay, wherever you find theta, that corresponding axis will be your E cos theta and the other one will be E sin theta. Okay, so now taking this case, I can say this is my theta I, right? So this KIZ will be my cos theta component and my KIX will be my sin theta component, right? Similarly here, this is my theta R, so this KRZ will be my cos theta component and KRX will be my sin theta component. Similarly here, this is my theta T, so this KTZ will be my cos theta component and KTZ will be my cos theta component and KTX will be my sin theta component, right? And coming back to the condition that KIX should be equal to KRX should be equal to KTX, we will write here. I can write KIX, that is the propagation vector of incident wave along the x-axis, is equal to the propagation vector of reflected wave along the x-axis. I can write it right. That, which I can write it as modulus of Ki into sin theta I, right? So this is my KIX. What is the modulus of KIX? That is Ki, because you are splitting Ki into the two components KIX and KIZ. So KIX can be written as what? Ki into sin theta I. Similarly, KRX can be written into KR into sin theta R. And we know what is modulus of our propagation vector, that is beta. Here it is written modulus of propagation vector K is beta. So that I can write it as beta 1, because Ki is your incident wave which is in your first medium, into sin theta I is equal to, what is the modulus of your KR? That is also beta 1, because your reflected vector is also in your first medium. So I can write it as beta 1 into sin theta R. So this beta 1 cancels. I will get sin theta is equal to sin theta R, which can be written as theta I is equal to theta R. That is, incident angle is equal to reflected angle. Similarly, you can write KIX equal to KTX. From that I can write amplitude of Ki sin theta